You can solve for the concentration of everything at equilibrium. What makes this question that I'm about to go over different than what we did last class is the acid is a diprotic acid. If you can't see it, it's H2S. When you have more than one hydrogen, there's a good chance that more than one hydrogen can be donated. However, the ability to donate the first hydrogen is not the same as the second hydrogen. That's why at the end of this question, two K values are given. One is 9.5 times 10 to the negative 8th. The other one is 1 times 10 to the negative 19th. First off, before we get into the mathematics of it, notice that the second K value is a lot smaller than the first K value. That means it's harder to lose that second hydrogen than it is the first hydrogen. That statement is true for all acids. Now remember, sulfuric acid, for example, H2SO4 is a strong acid. That means when it loses its first hydrogen, it just does it completely. But there is actually a K value for sulfuric acid's second hydrogen, because after it loses that first one, it's no longer strong. It's now a weak acid at that point. So this calculation of solving for the pH of a diprotic acid, or what's the concentration of everything at equilibrium, is the very last question of web assign coming up. So the web assign that you're doing for next class is more of this type of math. It's not going to be anything of the last topic that we're covering today, because again, I'm not sure how far we're going to get through with that. So, yes, jumps out of there. There's my initial concentration from that problem. Excuse me. That. Again, normal ice table. So far, so good. This problem is pretty simple. Okay, so now we do products over reactants equals K, just like we've done before. Products are x times x, which is x squared, over 0.0250 minus x equals, and since this is the first loss of hydrogen, this is going to equal the 9.5 times 10 to the negative 8th value. Remember, the good news with this problem is that the molarity is significantly different than the K value, so we can get rid of the minus x to simplify this. And again, we can go over all the simplification math if you choose to do. Multiply both sides by 0.0250, take the square root of both sides. Again, if we just kind of speed this up a little bit, I'm going to give you the x value. So again, hopefully you're comfortable with isolating the variable when you have x squared over 0.025 equaling something. So the x value for this is 4.87 times 10 to the negative 5th. Recall what that means. That means that's how much of the HS minus I have. That's how much of the H plus I have. And if I take that number and I subtract it from 0.0250, that would be how much of the original acid remains. Kind of like the problem I showed on the whiteboard from the last web assign question. You solve for x, remember that x means something. The ice table is there for organization purposes. Now, if this were the type of problem that we did last class, and it was asking for the pH, you would take the negative log of this value right here, because that's your H plus concentration, and you'd be done. But after this has occurred, I still have something that can donate a hydrogen. And that's what makes a diprotic, di meaning two, protic meaning proton, a diprotic acid different than a monoprotic acid. So, we need to do more work. We're going to extend this a whole bunch. Because that HS minus can donate a proton. Initial concentration of HS minus, that's that 4.87. Remember we solved for X and that was the X value? Initial concentration of the H plus, that's that 4.87. We already solved for that. And only the sulfide ion is 0. This will lose a certain amount we call X. This gains a certain amount. This gains a certain amount. Hopefully you're okay with me using X, even though that X value will not be the same as the part 1 X. So if you don't like that, you could choose a different variable. I don't know. Isn't X the variable? So here's my ice table to finish up that point. Again, what makes this different is if you can donate a second hydrogen, we have to account for how much of that will contribute towards the pH as well. So, products over reactants. Those are my two products. Divided by reactant. And the K value for this one is really tiny. Now, this could end up being a beast to solve for. Multiplying the X through, multiplying both sides by the denominator, get anything on one side. This has the makings of, oh no, I gotta use the quadratic formula. If it weren't for the fact that we can once again use the shortcut. Because the difference between our concentration, which is 10 to the negative fifth, and our K value, which is ridiculously small, means that this addition of X, or this subtraction of X, is such a minuscule number, we don't care about it. Now, you can't get rid of the multiply by X because multiplying by a small value does significantly change it. But subtracting a tiny value from something doesn't really make a difference in what it is. But now, ladies and gentlemen, now that I got rid of the plus X and the minus X, what else can I simplify? Same top and bottom, right? Basically, you just solve for X equals the second K value. So, if pH is the negative log of H plus, I need this value to solve for pH. Now, if you were to take that tiny K value and add it to that number, your calculator is just going to give you this number back again. Because it's so minuscule. Not every weak acid has the second K value significantly less than the first, like this problem did. So much so where, what's the point? But if I were to solve for pH, it would equal the negative log of, what was that number, 4.87 times 10 to the negative fifth. Remember our rules of logarithm then. 10 to the negative fifth is representing the power of 10. That's the number in front of the decimal. I have 3 digits here. I should have 3 digits after the decimal. That would be the pH. That's not the only thing that this question asks for. It also asks for the concentration of the H2S, the concentration of the H+, the concentration of the HS-, the concentration of the S-2. And that's what the last WebAssign question is going to do for next class. It's going to ask you the concentration of everything at equilibrium. So, remember our H2S. It was 0.0250 minus X. That's our concentration at equilibrium. So if I give the concentration of H2S at equilibrium, I called it 0.02495. Now, I'm adding a sig dig just to show that it did change. I might end up having to call it 0.0250 if I didn't have a little liberty with sig digs. The HS-. If I look back at all my organization here, I originally solved for HS- being X, that value at the bottom of the screen. But remember, I set up a second ICE table. But if I take 4.87 and I subtract that tiny amount, it's going to give me that. Similar thing can be said for the H+ concentration. The only thing left is that second conjugate base, the S-2. And for that particular problem, remember, here's my ICE table. The S-2 equals X. And what was X? The second K value. Here's what I would say. You could go through all of this work if you wanted to. Otherwise, if you realize that the second K value is a lot smaller than the first K value, it's basically not going to be changing this stuff much. So if it asks you for the pH and the K values are significantly different from each other, do the first round of your pH math. And when you solve for X, which will be your H+ concentration, that's going to be what you use to solve for the pH. On the WebAssign, it is going to ask you to solve for everything at equilibrium, kind of like I have shown here. Instead of mathematically trying to show what the second conjugate base's concentration is, trust me when I tell you it's going to equal the second K value. So you don't have to do the math. We did the math. If you don't believe me, we can do the math again, because you're going to do a practice problem with this in a little bit, and it's going to give you the exact same thing. That when those K values are significantly different, that second one is more or less going to be the concentration of that second conjugate base. So when we started this unit, we went over 2 definitions of what makes things acids right away. One was creating that hydronium ion, that H3O+. The other is it donates a proton, the H+. At the very end of that introductory reading guide, then it asked what a Lewis acid was. And more or less, if an acid gives an H+, it can accept a pair of electrons in return. And I drew out a little bit of Lewis dot to try to show that. That Lewis definition is going to lead us into things other than something that starts with hydrogen acting like an acid. And that's kind of the transition we need to move into here when we start talking about ions and how ions interact with water. Because the interaction with water, remember, water can act as an acid or a base. It just depends on what it's around, that term called amphoteric. the interaction with water plays a big role in this. So, first off, again, this is what we talked about with what makes something an acid, what makes something a base. Creates hydronium in solution. It donates a proton. A base creates hydroxide in solution, accepts a proton. Again, I could draw out the example like HCl. If you put HCl in water, what happens is a pair of electrons creates a bond to that hydrogen. So in essence, the HCl is donating that H+. Then this bond breaks and gives 2 electrons for the chloride ion. Very common base that we could talk about for a covalent base is ammonia. When ammonia interacts with water, kind of the exact opposite happens. Where instead of it losing a hydrogen, it's going to accept that hydrogen. So you can see how water is grabbing hold of the hydrogen from HCl. Water is donating the hydrogen for the NH3 example. So again, this is what we've talked about before. When I circle those electrons, that's the key to the Lewis definitions that I want to go over next. See a couple people drawing. I'll give you a second. Are you ready? Now, if I switch slides, does that picture stay? Oh, it doesn't. All right, so a Lewis acid accepts a pair of electrons. That's kind of the definition. My second bullet point says that that means an acid can be something without an H+. Vast majority of work that you're going to do with acids, they're going to have an H+ that leads off that formula. My third bullet point is showing you different examples or identifying different things that could act as a Lewis acid. When I say electron deficient, remember our bonding unit. An incomplete octet is something that doesn't have 8 electrons around it. An example of that would be boric acid, BOH3, which is what my third bullet point says. That's a tricky one. When you look at the formula BOH3, I would assume most of you had bells going off saying, wait a minute, it has OH in it. This thing is going to be a base. And I wouldn't blame you one bit if that's what you thought. But in BOH3, the boron bonds 3 times to oxygen, because it only has 3 valence electrons. Remember, boron, being a nonmetal with only 3 valence electrons, can't get to the octet. It's an incomplete octet. It's electron deficient. It is something that's going to readily bond with something in order to get to the octet. And when that happens, one of those hydrogens on that OH often gets donated out. That's what's going to make it end up giving a hydrogen. Because if you remember that polar pack we went over, acids commonly have an OH bond to them, and that's the hydrogen that's lost, especially those polyatomic ion acids. Polar double bonds, you actually saw last class. Carbon dioxide, C double bonded to O on both sides. That's a polar covalent bond. Even though carbon dioxide as a whole is nonpolar due to symmetry, if you remember that from our bonding unit, the bond itself from C double bond O is a polar covalent bond. And with that, those bonds will break. And then they can accept with water, and then water bonds with it. And really, it's their interaction with water. The one that I'm showing on the board that I want to kind of talk about is the one that you're going to see in the reading guide in a little bit. And it's the one that, in my mind, makes students really have to think of what's going on here. Some, not all, some metal ions will act as an acid. So, example, iron plus 3. Now imagine if I dissolved in water iron 3 chloride, FeCl3. It's an ionic compound you dissolve in water. You've been taught that, hey, you dissolve an ionic compound in water, it's neutral. Not this guy. What I show on this picture on the board is waters will surround the iron plus 3. Hopefully you remember drawing dissolving from Chem 1. In fact, they just finished that unit, where the oxygen is partial negative, so it's attracted to the iron. Especially with highly charged ions. Think about it. If Fe plus 3 is a big positive charge, that partial negative oxygen is really attracted to it. And that's what is being shown on kind of the lower right, like at the 4 o'clock position here on this. So much so that that attraction is almost kind of creating a bond. And when that oxygen starts getting pulled towards the iron because it's attracted to it, that makes it harder to hold onto a hydrogen. It's kind of like the inductive effect that was shown in that Pogel packet when you have something really electronegative bonded to the OH group. One of these hydrogen bonds are bound, or one of these bonds between O and H are bound to break when you have a highly charged metal ion in the middle, just because of how it interacts with it. So this is one that you're going to see on the reading guide in a little bit.
But if it just took the, like, if it broke one of the H's off, you have OH and FH?
It'd be like an FeOH type complex, and I think our book will even show kind of an equation format for that.
So because it's part of that, like, because it's part of that complex, the OH is not basic?
Correct. Because the OH is not dissolved on its own, it's kind of connected to it, because it would have to be free to be the base part. Now notice I have a lot of examples of Lewis acids. I have very little for Lewis bases, because the base is not as much of a point of emphasis as the Lewis acids are. However, you will see examples of how anions will create a basic solution sometimes. First off, my definition of a Lewis base is something that donates a pair of electrons against the exact opposite of the acid. And I actually don't know why I have this second bullet point here. I want to show you a different example on my last slide. I think this was an example I found from the last textbook that tried to talk about how those ions would play a role in it. But again, the key with both of these is usually, like with that metal ion, what's water going to do when it's around it? So here's what I want to end with instead. Last class, I mentioned to you that the ocean is basic. It has a pH above 7. And yet the more carbon dioxide in the air is lowering that pH slowly. Again, I have a graph that shows that back in 1988 when Eliza was many years away from being born at all. I mean, I was 10 years old then, Eliza. That was back in my prime. And my prime might have been, I don't know if I ever really had a prime. 8.12 is the average pH. And now in October of 12, so again, that's not even the most recent data. I just found this graph online. It dropped to about an 8.8, and some people say, well, or 8.08 rather. Some people say, well, that's a very tiny change. Who cares? The ocean is enormous, ladies and gentlemen. To get something that big, to dissolve that much acid, to lower its pH even a little bit, is significant. Now, my first bullet point, hopefully we realize this. If not, why don't you at some point take a road trip out to a coast? Go into the ocean a little bit. Let that water splash into your face. You'll taste the saltiness. That salt isn't just sodium chloride. That salt is from the earth being around a long time, and water and waves crashing upon land and dissolving things from the shore and making a slightly salt solution. The bicarbonate polyatomic ion is one of those things in that water. That's the bicarbonate polyatomic ion. If I were to draw it out in Lewis dot format, look like that. Do we remember the shape on the carbon? Trigonal, because it's bonded to three things. Planar. Do you remember the shape on the oxygen? Should be linear, but these electrons make it bent. Okay, back to this stuff. If I then drew a water, kind of like I did on the previous problem, sorry that I'm running out of room here. It grabs hold of that, it tracks that, creating hydroxide. So some anions in the presence of water can create hydroxide. And this bicarbonate, from what I've read, is the primary reason why the ocean is slightly basic. It's because its reaction with water, which is referred to as hydrolysis, something reacting with water.